first, you can pick up my slides if you want. We're in session 4. This is the 4th week of the semester. So there's 3 files that are 4. Start with 4. The ones that are important are the ones that are .r. So one is I'm going to give a short talk on smoothing of data, something called statisticians call density estimation. And then, well, you're the statistician, so you know that. The astronomers don't know that. They call it smoothing. But you have to pick up the density F4, density estimation.r file. It's very short, of course. The 4 time series.r, that's what we'll do in the second half today. And that one's more complex and more advanced. Okay. And maybe not as solid. You then also, for the time series one, you have to pick up 3 data files. 2 of them are called Kepler1 and Kepler2.dat. They're half a meg each. And then there's one called HD3651_RV.dat. It's dated today. All 3 of those are dated today. So if you want to, in fact, I bet you can find these files by doing last modified. I bet that will work. Yeah, there they are. Everything what was loaded today is on top. You can just load those 6 files, and that will bring everything you need for today onto your local, put it in a directory. Hopefully you have a directory for this course, and put it there. And we'll start using it in about 20 minutes. Okay, so the first 20 minutes I want to give a talk. And while I'm talking, you can download this. Any questions about the files? Okay, thank you. Okay, today is divided into 2 portions. One is smoothing the data. I'm going to give a little talk and then give a sort of a relatively elementary tutorial, R tutorial that I give elsewhere. And so it's polished and it works. Then we're going to have a break and have some coffee. I finally intelligently brought some cookies. We can go with the coffee if you need some sugar. I do, at least. And then I'm going to do a no lecture, but just R, of some more sophisticated time series operations. And we won't have time to study them, but it's more like exposing you to them. And then either you or I can talk about it more if we look into them more if we want to. Most of them are from a field called econometrics. Okay, I will start. This lecture, again, is designed for, this more elementary lecture, is designed for astronomy grad students. And since most of you are statistics students or postdocs, I'm going to go really fast, okay? But maybe you'll get something out of it. To me, what's interesting for astronomy and astrostatistics is this is the context within which a popular method known as Gaussian processes regression lives. So it's more context than advanced details. Okay, so what is density estimation and why bother doing it? So the goal of density estimation is to estimate an unknown probability density function called a PDF, which is smooth, it's continuous, of a random variable, or more than one random variables if it's multivariate, from a set of observations. So we start with so a bunch of observations, and we want to get a curve or a surface if it's more than one dimension. So it could be one or several random variables. An example being, okay, let's take planets. The masses of the planets, the ellipticity of their orbit, the radius of their orbit, those are random variables, okay? So it could be smoothing a distribution of random variables, a collection of random variables. Or you could measure a single quantity, call it brightness, let's say, as a function of a fixed variable. For instance, time. So time is not a random variable. Time, try to go back 5 minutes. Try to go ahead 5 minutes. You can't do it, okay? It's fixed, okay? So space, x, y, z in this room are 3 fixed variables. Right ascension and declination of an astronomical image are fixed variables. So images are random variable like brightness or color on top of a fixed grid. And time series. has a random variable, the brightness or the radial velocity or something, on a fixed variable. Now, just a side comment. I've looked at lots of textbooks in statistics. I've only found one textbook that says, here's a method, blah, 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 with some regression method or something for random variables. And then another section, here's the same thing for fixed variables. There has to be at least one random variable. but you know, and apparently it's slightly different statistically, but I couldn't quite figure out what was different. So I have a feeling that most statisticians think most of the time in terms of random variables. All of the variables are random. But when they do something called time series analysis, or they do something called image processing, then they sort of switch in their mind to a random variable as a function of fixed variables. And I think they don't care very much, they being your statisticians. Okay. But I would be very pleased if maybe over the break, one of you were to come to me and say, no, Eric, you misunderstood. This is how we think about fixed variables. Okay. So I'm not really sure. Okay. But in fact, time series analysis is related to image processing and also related to something called astronomical spectra, where we have brightness as a function of wavelength of light. And we do a lot of that modeling as well. And that's also a fixed variable. You can't switch them around. You can't juggle them. You can't go, you know. So in more familiar language, this density estimation, which is going from individual points to a smooth curve, it is smoothing. That's what astronomers call it and physicists call it. It smooths collections of individual measurements into a continuous distribution, replacing points on a line or a plane by a smooth curve or surface. Okay. Now, when you know the parametric form of the distribution, you know that the distribution has to have a polynomial form. There's a parametric family. Okay. Or you know you have some knowledge from astrophysical theory. Oh, it has to be. It has to trace an ellipse because it's a planet around a star. So it could be sort of a heuristic thing like a polynomial, or it could be astrophysical like an ellipse or something more complicated. Okay. Then we don't call it density estimation. Then the derivation of that smooth curve is called regression. And the goal is to assume the family, polynomial family, let's say, and to find the parameters, the coefficients of the polynomial. Or to assume an ellipse and to solve for the size of the ellipse and the ellipticity of it and its orientation. The parameters of the model. Okay, that's called regression. That's another lecture. It's another field of statistics. It's not density estimation. So really the word density estimation is usually called, or should be called to be more precise, non-parametric density estimation. Because if it's parametric, then it's called regression. Okay, so the name of the textbook in the field is non-parametric density estimation. At least a couple of them. Some of them sort of locally use little teeny-weeny polynomials locally, and sometimes that's nicknamed semi-parametric methods because it's not globally parametric, but it's locally parametric, and Gaussian process regression, if you happen to know that, is one of these semi-parametric methods. Some are fully non-parametric, some are semi-parametric, and they're in the titles of the books. So the titles of the books are really confusing because they don't, this adjective is not always there and not always the same. Okay, so there's lots of applications where we have individual points, we want to smooth them. A lot of them have nothing to do with time series, so I'm only going to talk about things that have to do with time series, so there's one that there, but this slide is mostly for astronomers. Okay, so imagine you had some observations and you want to find a continuous distribution. Okay, so these next two slides are basically things astronomers do that statisticians wouldn't do. Okay, and it's called making a histogram. Okay, so we have individual. This is univariate in this case. It's just measurements of asteroid density. 27 asteroids have their density known, and astronomers often just start somewhere and just bin them up. We call it binning, which is statisticians call it grouping into evenly spaced sort of intervals. Notice it's exactly 0.5 width here. Why is it 0.5? I made it up. I made up the bin width. Why does it start at 0 or 0.5? I made that up too. Astronomers are doing this, I mean, I would say 100 papers a month have arbitrary binning. I mean, it's still totally common. By the way, it's perfectly nice to visualize things. But here's another binning algorithm. This one has a fixed number of asteroids in the bins instead of equally spaced bins. So how do you know which one to do? And the answer is you don't. Also, it's not a very good physical model. It's continuous. It's continuous in X, but it took individual points and it made them continuous in X, but it made them discontinuous in the frequency. Okay, and those discontinuities don't exist in nature. And there's no mathematical guidance for choosing the binning method. And once you have a bin, you don't know how to choose the center of the bin to make other inferences. And basically, all the textbooks in non-parametric density estimation have chapter 1, histograms, and they end chapter 1 with statements like, no, I'm not good at a British accent, but imagine I was a distinguished British statistician named Bernard Silverman. In terms of various mathematical descriptions of accuracy, the histogram can be quite substantially improved upon, which is British for saying, don't do it. Okay? Here's an American. The examination of both undersmooth and oversmooth histograms should be routine. It means you just guessed the width. So you better try a few more and see if there's more features or, you know. Basically, don't do inference from histograms. They're used for exploratory visualization of univariate data, maybe bivariate, but not recommended for statistical analysis. And if you want to actually fit, let's say, parametric models, then fit the original data. Don't fit the histogram. And unless the data happen to be actually come out of your instrument in ordered fixed categories, some instruments actually produce histograms. I mean, that is the data. But most instruments are not, or the bins are so narrow we just don't consider it to be histograms. So these two slides are warnings to the young astronomer, the old astronomer too. We've been doing this for about a century or so. I don't know when we started histograms, but you'd be surprised how much statistics is done erroneously on histograms. Okay, so what does the statistician say you're supposed to do for smoothing if you're not going to use histograms? And the answer is, I'll use two phrases, statistician's phrase. Kernel density estimation, astronomer's phrase. Convolve with a Gaussian. It's the same thing. Perfectly good. They recommend this. Astronomers know this, so that's good. So the most common non-parametric density estimation convolves discrete data with a normalized kernelized function to get a continuous estimator. So there are the individual points. There's a continuous variable x there over here. And you convolve with a function that has a parameter called h. That's the width of the Gaussian. Okay? There's some rules. The kernel has to be integrated to unity. It has to be symmetric. There's some things. Now, a Gaussian is a perfectly good choice, but it's not the best. The actual one that has the minimum variance is called the Ipanichnikov kernel. And at this point, I turned to all the astronomers. I said, how many of you have heard of Ipanichnikov? No, zero. Have you?
I came across it last.
There we go. He came across it. Okay, so almost no one's ever heard of it. It actually is an upside down parabola. So it's 0, then a parabola, then 0. Whereas a Gaussian is from minus infinity to infinity, it's never 0. It's low, and then it goes up and down. But they're very similar, and it almost doesn't matter. The main thing that the astronomer has to know is that don't use the uniform kernel. 0, 1, 0. We call it the boxcar. It's also known as the Heaviside function. That one actually is not a good smoother. Okay, so choosing the function is easy, just use a Gaussian, but choosing the width of the Gaussian is tricky. And this is where the astronomer basically doesn't know how to do it unless they happen to learn some statistics. Okay, but the statistician does. So there's no formal rule about how to do it, but there's a very strong recommendation that by the statisticians to minimize the L2 risk function known as the mean integrated square error, or the MEES. So the minimum MEES, choose a kernel width such that the MEES is minimized. And what is the mean? Well, it's that the estimator, that the smoothed estimator, the kernel smoothed estimator, the hat there is estimator, minus the unknown true function quantity squared, the estimator of that, the average of that, is minimized. And this theorem, or this sort of mathematics, is written down in textbooks. There's a cute little textbook by a top American professor named Larry Wasserman at Carnegie Mellon called All of Non-Parametrics. It's a little book with bright pink cover. It's a very strange little book. And it's called All of Non-Parametrics. And he teaches it to non-statisticians. He has another one called All of Statistics. That's a little arrogant, Dr. Wasserman. All of statistics in one thin book. So this is the way he teaches, let's say, computer scientists, intermediate level statistics. It's good for astronomers. So it ends up, if you read the theorems in there and stuff, this thing, what you're minimizing is the square of the bias plus the variance. And in terms of its bandwidth for the Gaussian, this one goes as h to the 4th power, this one's going to h minus 1, and you can minimize this. Obviously, there's a single value of h that's going to minimize this sum. So therefore, it should be easy. You just sit there and do a little calculation, you can do it. The problem is, these constants c are unknown and sort of unknowable. So you can't really formally minimize it, sort of analytically. Okay? Because it depends on the integral of the second derivative of the true PDF, and it therefore is unknown. So you got to estimate them. So how do you estimate this width? Well, if you want to read Bernard Silverman's famous early book from 1986 called Density Estimation, very cute little book, then he gives a rule of thumb that says as follows. Take the standard deviation, or if you wish, the interquartile range, and minus to the 1/5 power of the number of points, the 1/5 power, see, the 5th power, that's the dependency on h. And multiply by -9 because it's a rule of thumb, and then you get it. Okay, and here's how you go to higher dimensions, where p is the number of dimensions. So this is, you can sort of guess for sort of simple things how to smooth things, but they're just guesses. They're sort of like choosing a histogram width. It's not really very official. There's no statistics. But in the 1980s, statisticians developed a whole apparatus. They developed two things. One was the bootstrap, and Professor Babu, Jogesh Babu, was really involved when he was a young man in the theory of the bootstrap. And but they also sort of a related thing called cross-validation, and these are theorems. It shows that you can sort of formally, correctly estimate. You can't get it exactly. A bandwidth from the data itself by resampling the data over and over and over again in a particular way. So one of them is called leave one out. Oh, I spelled it wrong. Leave one out. Leave one out samples. So you have n leave one out samples. There's the leave one out samples, and these are kernel smooth, and you get this cross-validation function, and then you minimize. You find the h that minimizes this particular sum. It's not an infinite sum. This is calculable. It's computationally heavy to do it if n is a large number and the large data set's huge. But you can do this. This is calculable. And there's a lot of variants of it. There's least squares cross-validation and generalized cross-validation. And they're related to other things, and I'm not a very good statistician. I'm sure if you take a graduate course in non-parametric statistics, you learn this page very, very well. And I've never taken the class. I don't know it very well. Okay. But the point is that to me, as a practitioner, is that they actually have real methodology based on something called cross-validation. So here is an example. This is a page from Wikipedia. Okay. The pale gray is a perfect Gaussian, and the blue little dots are randomly sampled from the Gaussian. It's data points. And now, given those blue data points, the red is an example of undersmooth data. It's too bumpy. It's too noisy. So the H was chosen so that there's too much variance. The green is one that's chosen where the H is too broad and there's too much bias. It misses the peak and it gets the wrong shape. And the black is the smooth with the H of that value that is the minimum, that minimizes the me's. It minimizes the sum of the bias squared and the variance. And so in this cute example, you can see that the black comes pretty close to the theoretical gray, and the red and the green are lousy. Okay, so that's Wikipedia. Thank you, Wikipedia, for giving us an example of this. Okay, now astronomers rarely recognize that when you smooth things, you don't give up error bars. The one reason the astronomer likes to do a histogram is that they know how many objects went into the histogram, and they take the square root of that and they get an error bar on it, and they do usually not very accurate statistics on using the error bars. But you can do confidence bands around kernel density estimators as well. For large samples and simple behaviors, it comes straight out of asymptotic normality, and it's easily calculable, and our calculations give it to you. That's a constant width confidence band, but a little more reasonably is to use the bootstrap, because the asymptotic properties may not be accurate. And this both accounts for small n. You don't need large n like you do up there. But also, your data set may be weird, and the bootstrap will capture the weirdness of your data set. Okay, now astronomers, they actually know about convolving with Gaussians, and so they actually do kernel density estimation moderately often. They're not aware that histograms are so bad, but they often have complicated features. They often have a distribution that's sort of smooth here, and then all of a sudden has interesting structure and then becomes smooth again. A very good example is you have a background that you're not interested in, which is constant or slowly changing. And then you have all sorts of features that do interest you. In an image, it would be a galaxy inside of a black sky. In a time series, it would be some sort of an event, a flare or an explosion in an otherwise uninteresting time series, like nothing, just noise or something. So what we often want is an adaptive smoother. So when the data actually represent the underlying function is smooth, we choose a big bandwidth. And when all of a sudden something very complicated and rapid happens, we want a small bandwidth. And that's called adaptive smoothing. So you open up Silverman's book, and you open up Wasserman's books, and you learn about non-parametric density estimation, and do they give you a beautiful chapter on adaptive smoothing? No. You lousy statisticians haven't solved the problem. There are apparently no good theorems, or very few, on adaptive smoothing. So there's no consensus on how to do it, unfortunately. This is an area ripe for improvement. If any of you young statisticians want to get happy smiles in the astronomical community, write some theorems on adaptive smoothing. Okay? So the only one that I found that actually seems to have a theorem is by Abramson, Annals of Statistics, 1982. It actually has a minimal me's for certain situations and zero bias. And here's the procedure. I think it's really cool because it's so simple. And apparently it has a theorem for some situations. Okay, the theorem is as follows. The procedure is as follows. Take your data set, use cross-validation or some other rule of thumb, but cross-validation is probably the best, and generate a single value of h that minimizes the me's, and convolve your data points with that, and get f hat. Then do it a second time. Take the square root of f hat, of this first smooth estimator, at each value of x. And use that, but you got to take it at 1 over the square root. That's the theorem, is the square root. And get a new locally changing value of the kernel width. And then do it again. Then convolve it again with the new adaptive width. You do it twice. First you do it with constant bandwidth, and then you do it again, and it makes it, as you get higher signal, it shrinks the bandwidth by the square root of the value of the first one. That's sort of simple. It's cute. There's one CRAN package that does this. It's not commonly done, apparently. I don't know why people don't do this all the time. Silverman has a more complicated one, but he doesn't seem to have a theorem. I think he just invented it. I'm not sure. Maybe he does. He's brilliant. He's one of Great Britain's greatest statisticians. So maybe that's a good one. I don't know. Someone should tell me. And then there is another one for an adaptive smoother, which is more coming out of the field of, I don't know what to call it. I don't know if it's called machine learning or computer science. Okay, but it doesn't have a theorem. It's not even smooth. And it's really, really, really simple. It can be done on gigantic big data sets. It's called the KNN smoother, K nearest neighbor. And it's incredibly simple. For each value, for each data point, for each value of x, just take x and microscopically go along x, find the distance to the kth nearest point, where k is an arbitrary number you make up. The 9th nearest point, the 3rd nearest point, the 29th point, I don't know, just choose k, okay? So k is essentially like this bandwidth, okay? So there's no guidance on how to choose it that I know of, okay? And so you go along, you find, oh, the 9th one is this far away, and so that is just 1 over that. That's the estimate over this, some scaling and some normalization. And you go along x, and it sort of hops along, it jerks along, and when you have a lot of data, then k becomes very small, and 1 over a small number is a big number. And when it's all spread out, then the distance becomes very big. 1 over a big number is a small number. And so it has the right behavior. Okay, and I guess I don't know enough to know the theorems behind it. Apparently it's related to the kernel density estimation with a uniform kernel, but I told you 5 minutes ago the uniform kernel is not recommended. So it's choppy. It chops, it jerks around like a histogram. But it's sort of cute because it's really simple. But I like that one. That one's simple. This one's more complicated. I don't know. I want somebody to tell me about adaptive smoothing and write a paper in the Astrophysical Journal teaching astronomers how to do adaptive smoothing for time series, for images, for any weird random variable they have. Because we need it all the time, and it's not in your textbooks. Okay? Adaptive smoothing. Time series is one of the interesting applications. Imagine you had an unevenly spaced time series. You want to adaptively smooth it. Makes a lot of sense. Or you have a relatively evenly spaced time series, but the behavior is slow and then rapidly changing with a lot of signal and then slow again. You need an adaptive kernel, adaptive smoother. Okay, there is something. I have a little trouble. I've just discussed something called non-parametric density estimation. Now I'm going to call something called kernel regression. They seem to me to be awfully closely related, but they have a different sort of foundation. Regression is sort of conceptually written as follows. The expectation of the y value, let's say the brightness of the star, as a function of the x, let's call it time, that's a time series, is a function of time. Oh, that's a dumb one. Of course, y is a function of x. Okay. So, but when you sort of write it this way, a reasonable estimation approach, if you have a data set that's not infinitely perfect, is to find the mean in some window around the value x, and the width of the window might be h. The same bandwidth we've talked about before with Gaussians. And you, once again, can choose h to balance bias squared and to minimize the sum of bias squared and variance, or to balance the contributions from bias and variance. Okay. So, so you can just choose a window and just choose the mean, but a more effective way might be to smooth it locally. So you might choose some kernel, for instance, a Gaussian kernel, and smooth the y's locally, and use the mean value of the smooth. Basically, do the same thing after smoothing. This is called kernel regression, and it's a form of local regression. There's a lot of local regressions. We're going to see some in just a few minutes. Okay. So how do you decide which one's best? Well, you might maximize the likelihood or something. Okay, so let's look at, okay, here it is. There it is. It's really simple. The estimator of the y, in this case it's called r here, is the sum over the data of the value of y convolved with a local kernel, just normalized by the kernel. And this was written down by two people simultaneously, I think in 1962. And one of them was named Nadaraya, and one of them was named Watson. Are these well-known statisticians? I don't know. And it's known as the Nadaraya-Watson estimator. And it's in Wikipedia. I mean, this is famous. It's well known. Okay. So here it is. Here's a simulation from Wikipedia. The green is the theoretical. It's a sine wave. The blue dots are points that are sampled off a sine wave with some Gaussian noise. Here's an Ipanichnikov kernel, a local upside-down parabola. It could be a Gaussian instead if you want. And it's looking at these points and it's weighting by this kernel, and it's saying, well, what's the weighted mean of those? And it gets this red point. And you just go along microscopically and calculate those red points with locally smoothing it. And you get the red curve, which is awfully close to the green curve in this simple example. Now, h is important. So if h is too fat, then and if h is too skinny, it's too noisy. It's the usual thing. And so you solve again for h using cross-validation to minimize the me's or something like that. So there's some variants of this. One of them is to not say I want the mean there, but to fit locally a polynomial. I mean, a mean is a polynomial of order 0. One would be to put a line there, and that would be a linear fit. Another is to put a little tiny parabola there, and that would be a second order parabola. And these are called local polynomial smoother. So actually the one on the previous page is a local polynomial smoother. It just uses the 0th order. And the most famous of these has two famous names. They're very old techniques. One of them was developed by an applied mathematician, a statistician named William Cleveland, who wrote a series of books in the 70s and 80s and 90s on this. And his method is called LOIS. It's a local polynomial smoother. And if you actually go and you use Google and ask what's the most popular smoother in industry and among practitioners, LOIS is always the winner. More people use LOIS than any other smoother. Okay. The new one actually includes some bells and whistles. Let's say that there's a point way down here, an outlier. Well, there's an M estimation robustness put into it and stuff like that. But once again, the width. Cleveland doesn't tell you how to find the width. You got to guess. You try it out till you like it. So the big problem with kernel density estimation is choosing the widths, the h's, whether they're constant or whether they're adaptive. It's always not so easy. Now, independently, a completely different group of practitioners known as geologists wrote down a local polynomial regression mostly for 2 dimensions. So it was a random variable in 2 dimensions. Let's think of this table here. So imagine I was interested in, that the height of the mountains, a contour map of the mountains. I'm a geologist, okay? Geographer, geographer, okay. Or here's one, watch this. I drill deep holes. And I say, here we have dirt, and then we have shale, and then we have, I don't know, granite, and then we have oil. Okay, so they drill for oil, unevenly spaced, and then they map the underground surfaces of the granite and the shale and the oil. That's how they find oil. It's worth a lot of money, okay? So petroleum geology uses kriging. Kriging is named for Mr. Krieg, a mining engineer from South Africa in the 1950s. It's old. they've been doing it for half a century, kriging. Somewhere along the line, the statisticians came along, a Frenchman named Mathurin wrote a whole book on this in the 60s or 70s and said, oh, wow, these geologists have been doing this. What is it? And it ends up, it's a perfectly good least squares maximum likelihood estimator. Nothing wrong with it. It's not even very special. If you would ask the statistician, they'd probably recommend it. It's a perfectly reasonable way of mapping things. The interesting thing in kriging, and there's some technology, it actually gives you not only a map of the mountains, but also a map of the uncertainty of the mountains using a Gaussian scatter hypothesis, which is very similar to Gaussian processes regression. In fact, Gaussian processes regression, which is now very popular in astronomy, is a smoother that also is a local polynomial least squares maximum likelihood smoother. And it ends up, it is kriging. So if you go to Wikipedia and you carefully type in Gaussian processes regression, carriage return, it looks like a mistake. It takes you to a page called kriging. So I didn't want kriging, I want the GP. Sorry, it's the same thing. Okay. So Gaussian process regression, which the astronomers seem to quote one book, Rasmussen and somebody, one strange book from machine learning. As far as I could see, it's just another formulation of Mathurin's MLE formulation of Krieg's original just heuristic method that was right. Well, it was a good method. So this stuff has a 60-year heritage, and astronomers don't seem to know that. I don't even know if statisticians know that. I think the method is not that interesting to professors of statistics. It's just so obvious to them. Yeah, you have a 1 or 2 dimensional, irregularly spaced sampling, and you want to do local polynomial regression. It's just the Nadaraya estimator. I don't think it's very different from kernel estimation. Maybe it's slightly different. Maybe it's elaborate. It's an elaboration of the Nadaraya-Watson regression, I think. So with some assumptions of Gaussianity, I think that's the important thing. There's no assumption of Gaussianity in that formula. That's just a procedure. It's an estimator. Kriging has an assumption of Gaussianity, and it's a little more complicated. Okay, now there's another one that also has an old history. It locally uses polynomials, usually parabolas, and you sort of take a bunch of local points and you fit a parabola to it, and then you move over, and then you maybe to some other spot, and then you fit another parabola. And the whole trick is to get the parabolas to link together, to not only have the same value, but the same first and second derivatives. So it becomes smooth. And the ability to sort of patch together smoothly parabolas in this way was developed by this man, de Boer, in this paper in 1972. Oh no, he's not the original guy. Who's the original guy? He's one of the most famous applied statisticians of the 20th century. Getting the algorithm for getting the parabolas to become smooth was a tour de force of applied math. It's an algorithm, it's not a statistic. Okay. And so what they did is they just said, well, forget where the data points are. We'll just choose locations. We'll call them knots. And we'll just calculate these parabolas with respect to the knots. And we're going to call that a spline. And when I was a young man, a student, an undergraduate or graduate, I heard of splines a lot. Splines were the technology for smoothing. Okay. I think that's the original guy, de Boer. National Academy, very famous paper. There's like quadrillions of different splines. Bezier curves and natural splines and B-splines and NURBS and M splines and I splines and T splines and box splines and spline wavelets. There's books, most of the books are from the 1980s. There's a stack of books up to the ceiling on splines. And you might say, well, you're younger. He says, you've probably heard of splines, but do all your friends use splines every day? No. They went out of favor. The reason they went out of favor is this pre-specified knots. There's no rules, or were no rules, to tell you where to calculate them. You just made it up. So people just got tired of them and said, this is just, it's not that it was wrong, it just didn't have an established procedure. So here is an example. This is from a distinguished statistician at Carnegie Mellon, Richard Cass. Here's a data set that is sort of slowly changing, then rapidly high amplitude changing, then slowly changing. That's the hard one to smooth. Because if you choose a constant bandwidth, let's take this red dashed line, that it has too many wiggles here, and it didn't quite get the peak, and too many wiggles there, and it just didn't work very well. Okay. If you choose a bigger bandwidth, it just misses the peak entirely. But you'll see by his straight one, his solid line, he got it. Okay? He got it slowly smooth here, and then rapidly went up, got the peak, rapidly came down, and became smooth again. Hey, Cass, how did you do that? That's cool. Okay? So this was not easy to do. This was done in the 2000s. He improved splines to this level. So how did he do it? Well, the modern techniques start with a lot of knots, and they prune them down using some sort of a likelihood criterion. And that's the trick that's now, I don't know if it's actually reviving splines in terms of utility, but it really revives it in terms of look how nice it can do. This particular one by Cass is called BARS, Bayesian Adaptive Regression Splines. BARS. I think astronomers should use it. I think BARS looks pretty good to me. We have a lot of data that looks like that. Okay, so I think we should run things like BARS. Cass is a little lazy. I've never met the man, I shouldn't say this, okay. But he didn't write a CRAN package, he just put his R code on his website. It's been sitting there for 15 years. So frankly, somebody should put it in a CRAN package so everybody can use it. Install that package, okay. So it's a little lazy, but aside from that, as far as I know, this is perfectly good. I haven't used BARS myself. Okay, so there's a large literature on this. There's a huge, forget about even the old literature on splines. In the last few years, we have multivariate non-parametric regressions and visualizations with R by a finance person. Local regressions and likelihood, a little more theory, a little more statistical theory by a statistician. Geostatistics, modeling spatial uncertainty, is in one of the recent books on Kriging, which of course is Gaussian process regression, which is one of the smoothing techniques. And there's an old one by Rupert, Wand, and Carroll called semi-parametric regression, because the little parabolas in there, so they call it semi-parametric. And the good news is that Rupert is rewriting the book, second edition, right now. It should come out in 2017 with R code, because when he wrote it, there was no R. So Rupert and Carroll and Wand are rather distinguished professors of statistics. Okay, Rupert's at Cornell, Carroll's at Texas A&M, and Wand, I think, is New Zealand or Australia or something like this. They're rather famous. Okay, Wand has another book on it, and big R packages that are very, very well used, like 50th version or something. So these people, in terms of the prestige of the statisticians, this is the most prestigious book, but it was the obsolete book until the new one comes out. Rupert, just for your knowledge, is actually working with astronomers. He's working with one astronomer named Tom Laredo. You may know Tom Laredo. Okay, so Tom and Rupert are colleagues. And then there's another book, because it's written by a Japanese person, it's not as well written in terms of the English, but I actually like it. It's very comprehensive. It has a chapter on histograms, says don't use them. It has a chapter on Kriging. It has a chapter on splines. It has a chapter on almost everything. It's amazingly, all with R, a lot of R in it. It's by Takazawa, Introduction to Non-Parametric Regression. In this case, the word introduction is an illusion. It's quite advanced. It's not, it's not advanced in terms of pure math. He just assumes you can read very dense things. Anyways, it's not truly introductory. And this is just some of the books in the library in this field. So astronomers know nothing about this. And I don't know about statisticians. I assume some applied statisticians know this very well, and some don't. I don't know. I don't know. OK, so now we're not having a break, because now we're going to do an R script that exercises some of the methods I just talked about. OK, we're going to do it quickly because I'm going to do it quickly. OK. Maybe not quickly. So if you have downloaded these files, we're going to do the file called r_densityestimation.r. No, for densityestimation.r. And an early version of this is in our textbook, but our textbook is really obsolete by now, so there's stuff here that isn't in the textbook. And I'm going to put that, because you can run RStudio or do what you want, but I'm going to run it there. And I'm going to put R on the other side of my screen. So I have only 2 windows instead of 4 windows, like RStudio. I'm going to start with a clean screen. There we are. I'm going to set my working directory to be my personal little working directory for this class, where I've put my data sets and my codes. This particular exercise doesn't use a data set. So in fact, I'm going to generate an artificial time series. But it's sort of like a little weird one. OK, first I'm going to call it x and y instead of y and time. But x is like the time-like variable. And oh, look at the teeny-weeny. Why did it come out so tiny? Oh, damn it. This happened before. Something's funny when I plug into your projector. My quart screen defaults in a strange way. Let me try to leave it and see if it will come back a little nicer. No, unfortunately, my plots are not going to be very pretty. They'll either be really tiny, or they'll have really tiny letters. It works perfectly when I'm not plugged into the screen, so I apologize for this. But this is just an arbitrary y. These are random numbers and stuff. So here I have 500 points, and they go from left to right. And they start off and they have a sort of a curviness to it. It's not a sine wave. It's not anything obvious. It's something nonlinear. And at the same time, there's a sort of a broadening of it. It's called heteroscedasticity, that the scatter is a function of time. And that, of course, is not a nice thing. You want to have homoscedastic data if you can, but astronomy data is often heteroscedastic, so this is not so uncommon to have something like this. But it's still, I just made it up just as an exercise to exercise some methods. OK, so section 1 is going to be a density estimator. A common one that's used is in a package called KernSmooth by WAND. I just mentioned WAND. So this is, I don't know if you know this, there's 10,000 CRAN packages, right? Something like 30 of them are so important and so well established, they deliver them when you load R in. And then you don't have to say install.package KernSmooth, although you can. It would still work. All you have to say is library KernSmooth, because it's already been installed, but it's not into your current session. So you still have to say library. OK. So there it is. It's version 2.23, and one was been working on it for 20 years, no, 10 years, I guess. And this is one of his kernel width. It's a constant width that I'm calculating here. It's something called a direct plug-in method. I haven't read Juan's book. I don't really know what direct plug-in methods are. Help DPPIK. Use direct plug-in methodologies to select of the bandwidth of a normal kernel density estimator. So it looks at the data, and it uses some method, which is not described here, proposed by these persons in 91 and described in section 3.6 of their book in 95. So the original was a JRSS article, a reliable, data-based bandwidth selection method for kernel density estimation. I can understand the title. I'm sure I couldn't understand the article. And I'm sure it has theorems. Okay. But this is a famous paper and then this is a famous book, Kernel Smoothing. Okay? And it's very, very easy to use. So we got it. It said, oh, in the x direction, we're going to assume, we're going to use 0.2, and the y direction, we're going to use 0.05. And now that we have our smoothers, we're now going to bin the data appropriately and use those two bandwidths for smoothing. And then since I have a two-dimensional distribution, smooth distribution, it's actually an image. So I'm going to use a program in R called image that actually shows images. And there it is. Oh, this one came out pretty good size. Oh, the letters are too small. So as you remember, it started off low and went down, had a dip, and then went big, and it broadened as it came out. So there we are. There's the image of it. I can do a contour map on top of that. Astronomers like images and contour maps, so astronomers like to see these contours, and maybe a statistician does too. To smooth your data, how do you display it? And the answer for 2 dimensions is an image with contour maps. Another possibility, astronomers tend not to do this, is perspective maps. So you take the 2 dimensions and you sort of, instead of brightness, you do height. And then it produces this sort of mountain or ridge in this case, and you shine the sun on it and it creates shadows. And so the perspective plot not only actually has the output from the smoother, this is the x, that's the y, and this is f hat. See f hat? That's the actual estimated value of the smoother. But you have to specify an angle this way, an angle that way, and where the sun is, and the shading, and a color. And it comes out really nice if you do a good job. So I fiddled with my angles so that it looks pretty. Sort of looks like a mountain climber might climb up, you know. Okay. And this one could be viewed as a contour map of a mountain. Okay. And notice how it sort of flattens out. It fattens, it's sort of broad, like the foothills of the mountain is that part. Okay, so there we go. We have done a simple non-adaptive, a simple a kernel smoother. We didn't actually use a cross-validation. I bet I could do it. Let me I'm going to say kern smooth cross validation kernel. See if I can find it. Oh, okay, I could have gone there directly. There's no cross-validation in here? I guess there isn't. This one doesn't have one. Whoa, local polynomial. I've heard of it. I can imagine that one. Okay. So this particular package doesn't have a cross-validation one, but there are lots. Oh, R has like dozens of kernel density estimation packages. So you don't have any trouble finding these codes. Okay. So now, thank you. We've now done a kernel density estimator with a single bandwidth, a single kernel, a kernel with a single bandwidth. Now let's do a spline. So this one is called a cubic spline. It's a very famous one. This one is a Fortran program from like 40 years ago by a statistician called O'Sullivan, who apparently is known. And these two gentlemen are the Stanford professors who are now extremely famous. This is probably when they were young. So this code is like an old classic code of spline fits. It's a cubic spline called, in R, it's called smooth.spline. Okay, so we'll say smooth.spline. I'm calling it cube-splo xy, cubic spline of x and y. I'm just calling it that for my own use. So first let me plot the data points. That's funny. I have it there twice. I wonder why. Okay, there are the data points. Oh, I see. I did put it there twice. That's odd. And shoot. You have to go to my web page and pick up today's files.
Yeah, I had trouble connecting to the.
Okay, could you ask someone else in the class? Okay.
Yeah, it was really here before, but do I know
Password?
Yeah, the password.
One number one. One number one.
Oh, okay. And that is for the Samsung.
Samsung case.
Samsung case. Okay, thank you.
Okay, so I then used the lines function in R to draw the curve that came out of cubic spline. And there it is. It's there in green. And it's flat, and it goes down, and it goes up. And I thought, hey, that's not bad. In fact, I'm pretty pleased. It got some nonlinear behavior in a reasonable way. Every time you do, there are many things you can do in R, which you can then run the predict function. Predict function is sort of a general thing. So if you're going to do a smoother, you can then ask the smoother, what's the value of the smoother at any given point? So you can give it a sequence of values and say, please tell me the value. And that way you can pull out the numbers. You can put it on the disk and run some other graphics or do something else with it that you want to do, or just keep it in R. Predict is a nice way of sort of coming out of the math and finding what the result is.
I have a question.
Yeah.
Going back to the smooth that spline.
Yeah.
Did you say how it chooses the word within that?
No. That's the critical question.
It's like a default.
Hold your breath. Right. I just let the default. Ready? So I asked the exact same question. I said, I wonder what knots it chose. And then I found out that I had to go into, I'll do it here. You got to say structure, str, of the output, which was cube spla xy is what I called it. And I had to look at all this stuff, and I figured out that deep inside of there, it had the knots. And if I'm very clever, I'll look and I say, 124 knots? So I decided I was going to plot them. So I did, because I had the same question you did. So I plotted them, and I made a rug plot, these little tiny plots at the bottom of other plots. They're really cute. Astronomers don't use rug plots. They're really nice. So I'm going to grab my little rug plot, and I put it in green on the bottom. And there it is. Ping, 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 brr, brr. That's the stupidest thing I've ever seen. Look at the function. It's just going up sort of gradually, and it has like 50 totally redundant knot locations. Ladies and gentlemen, that's why people stopped using splines. Because your algorithm for choosing the knots is sort of arbitrary and often stupid. And I don't mean to say that Sullivan and Hastie and Tibishwani are not distinguished statisticians. They are. But this old Fortran code they wrote in the 70s or the 80s is really sort of stupid. So I'm not saying it's wrong. It's just not very elegant. Okay, so being an energetic astronomer, I go and I look around R and CRAN, and I found another one. I found COBS, constrained B-splines non-parametric regression quantiles. And I decided, well, how do I know? I don't really know these people. So I read their documentation. So I found out that it started in 1980 with an article in ACM Transactions on mathematical software called Linearly Constrained Discrete L1 Problems. Okay. And then 15 years later, the author of it wrote an algorithm for quantile smoothing and computational statistics and data analysis. Okay. And then 3 years later, he and someone else, or she and someone else, wrote another one, COBS, in computational statistics. And then 8 years later, joined up with this person's well-known in R. This is one of the R core team members from Vienna. And they wrote a fast and efficient version of this, and they published in Statistical Modeling. So I figured, okay, there's been 30 years of refereed papers by applied mathematicians and computational statisticians. I guess I'll believe it. You know, it's okay with me. So I took COBS and I ran install packages. Here it is. Install packages COBS. I got to choose a mirror. I'll choose Michigan. Okay. That's funny. Yes. I don't know why it's compiling it with an error. Oh, that's terrible. That's not supposed to happen. It's supposed to work. Maybe it is there. We'll see. So I'm going to run COBS, and I find out that it's a rather clever program. Yeah, it worked. It not only is going to fit me a spline through, let's call it the middle of the distribution, which all the others do, but it's actually a quantile regression method. It's going to allow me to say, let's say the 10th percentile on top and the 90th percentile on the bottom. It can actually give me a range of them that allows for asymmetrical heteroscedasticity, which means it doesn't have to be symmetric and it doesn't have to be Gaussian, and the scatter can be weird. And hey, I'm an astronomer. I don't have Gaussian. My stars don't know about Gaussian scatter. So I actually like this, that it's a quantile regression technique, and it's smoothing at the same time. And then the other thing I like about it is that it says, performing general knot selection, whatever that means. I'd have to read the articles to find out what he means. Okay. Then look at this, deleting unnecessary knots. That satisfies me. I don't like 124 extra knots. So it's deleting them, and it's using a likelihood criterion. I forgot, AIC or something like this. I'm not a statistician. I'd have to read the articles and struggle through them and ask Yogesh advice. And I just don't have the energy for that or the skill. But I mean, this is a real method by real statisticians today to give a reasonable smoother, but not only that, but to do it in such a way that it can be it's the red curve now, but it also gave the 25. I chose 25 and 75 percentile things, and it's slightly asymmetrical, as you might imagine, to get the deep dip. I took the log here to make that dip asymmetrical. What I didn't like about it seems to have too much curvature over here. I like the green one better, but who am I to say? It's all within the confidence band, so it's not as though it's a mistake. And then I plotted as a rug plot in red the knots used by this program, and I was really shocked. I went from 124 overly redundant knots to only 3 knots. I thought, gee guys, can't you what about 10 knots or 20 knots, something in between? What can I do? One of them chose too many and one chose sort of too few, in my opinion. Well, it's just my opinion. These guys are mathematicians. So all I could say is, the spline stuff is not so, it's a little mushy, you know? Different people do different knots and get different curves, okay? So welcome to splines. Okay. Section 3. Same theme, same fake data. We're not going to do anything different. But we're going to use 5 well-established bivariate semi-parametric local regression estimators. That's what I gave my lecture about a few minutes ago. Okay. I gave some slides. You can look at it later that are on the website. That's a lecture on some of these methods. Okay. Yes. So here's the famous one by Cleveland called Lois. He wrote a book. He made a lot of money. It's extremely popular. Everyone uses it in practice. I think in industry. I think I would use it too. If I don't think there's anything wrong with Lois. Okay. And there it is. It started here and it went down and it went up. It had a little kink in it, and that kink was not in my function. Since I know what I did not put a kink in it. So that's a little wrong. So thank you very much, William Cleveland, for giving me a Lois fit. Let's look at the things. Oh, this took me a long time. I did this several years ago when I drafted the first book. I had to figure out the difference between order and sort. So if you run order if you want to have the sorted indices, and you run sort if you want to have the sorted values. And so this, I had to not use sort, but use order. And then Lois happens to like the data already sorted in the X variable. And then it uses a formula, what's called formula in R. That's the tilde. So the Y is now a function of X. And this span is like the H. It's like the bandwidth. You just have to make it up. You try one, you try another. He doesn't tell you what to do. There's no cross-validation built into Lois. So I chose 0.5, and that's what I got. I could try 0.4, I'd get something a little noisier. 0.6, I'd get something a little smoother. That's the way it is. Okay. Now I mentioned quantile regression when I did Cobb's a few minutes ago. Quantile regression was really developed by a statistician named Kunkner who wrote a book in 2005 that's so mathematically difficult I can't read a word of it. I have no idea what's behind quantile regression. It's clearly difficult mathematically. So I just loaded quantreg. Quantreg is really quite an important package. It's widely used in R. And I sorted, I plotted the data. There we go. In this case, quantreg is doing segmented linear solution. So instead of a curve, it did a line. And then it chose a change point and did another line, another line. It chose 1, 2, 3, 4, 5. So essentially, it chose 5 knots. But instead of fitting nice, pretty parabolas that smooth together, it did lines. And then it independently did a solution with different knots for the 25% and the 75 percentile. The dark one's the median, the other two are the quartiles. So I want to say to the astronomer that quantile regression is really powerful. I mean, we often have large data sets, we want to do regressions, but the scatter is not symmetric, the scatter is not homoscedastic, it's not Gaussian and homoscedastic, and quantile regression is the way to go. Okay? So, that's really quite powerful. Astronomers should definitely know about it. Okay, here's some more. I think these were economists, and they wrote a package called NP, which means non-parametrics, and actually NP was pretty cool, I thought. Because what NP did is that it did a local bootstrap for the local errors. So here it is. Here are my data points. Here's a curve that has a little kink in it again. But you see, it's hard to see on my screen. My screen's not very good here. But it's really very accurately known on the left. And then it gets bigger and bigger error bars as you go right. Now that's what I built in. I built in that heteroscedasticity. So I really like this. And this is done by within the Windows. It's doing bootstraps, and so that's a very nice technique. I don't like their plot. They have an automatic plotter that is annoying in my opinion, but what can I do? Then this particular one, I wrote it down. 200 people are downloading this package a day. I mean, this one is clearly being used. It's called LockFit, local fitting. And this one is really powerful for astronomers because it allows heteroscedastic weighting of the data points, which means unequal error bars. It allows upper limits. This is called censoring of the data. And it treats outliers and has all these important bells and whistles. This is a really, really nice code. And it's not just one line. I mean, there's lots and lots of options to it. So I'll just run it in once, but it's really cool. And it's called LockFit for local, and there's a book that they wrote. And so I got to load it in from CRAN. And it ran, boom. And these things don't take very long. They run very fast in terms of CPU time. So let's see what LockFit did. It also allowed me to do the N.7.3. What am I doing here? I think I did it twice. Let me just do it once. NN must be sort of like KNN. It's sort of a bandwidth. So there's a smooth one. There we go. NN with 7. It was too smooth. It didn't get the shape right. So I decided to try NN of 0.3. As you can see, I'm just guessing the bandwidths. And that one has too many wiggles. Okay, but the nice thing, again, is that it gives the confidence bands really quite nicely around the median curve. Okay, so then I tried Gaussian processes regression. There's the book that astronomers are reading. I'm using the version in Kernel Laboratory, I guess. I don't know what Kernel means. It's one out of, there are so many packages in R for smoothing. It's ridiculous. And I was very irritated at this code. It's called Gaussian processes. So it used a polynomial, a 5th order polynomial. And this is the default. Obviously, I could change these things. And here's my cross-validation parameter. I told it to do 10 cross-validations. Here's the cross-validation error. Here's the training error. Here's this and here's that. And all sorts of things. It's really quite elaborate in terms of the internal mathematics of this. It's not that simple. And there it is. And then I said, please give me the confidence band around it. And it did a terrible job. I'm not even going to show it. And I don't know why. And I've complained about this to someone. And someone said, yeah, R doesn't have a very good Gaussian process regression code at the moment. So here's a couple others that are out there. Maximum likelihood estimates of Gaussian processes, MLEGP, and GPTK, Gaussian Process Toolkit, and there's a tutorial in an R blogger's comment that's a collection of all the blogs. I don't know if you know, R has like 500 blogs, and rbloggers.com collects them, and you can search them. So, and they wrote their own. In the blog, they wrote their own Gaussian process regression in R. And so this is just a hint for those of you who might be interested in GP regression and you might be interested in R. And since I've now spent about 20, 30 minutes showing you all these different versions of things, I got so confused, I decided to write a version that put them all on one graph. And I'm sorry, I'm supposed to have a legend. Where's my legend's tiny. Okay, I'm sure your screen is going to have a nice legend. You have a great legend. Yeah, you can read your legend. So the legend says, well, the green one is this, and the yellow one is this, and the red one is this, and those error bars and these ranges. And basically, for my toy data set, my real opinion is they all did a fine job. You know, there's nothing wrong with them. Okay, the red one curled over too much over there. You know. And the yellow one has too many wiggles over there. So they're not all identical, but they're all easily within their confidence bands of each other. So in other words, for the particular problem I showed, everything I've done has been sort of overkill. I just had like 6 methods of smoothing that gave essentially the same smooth. Okay, so maybe it doesn't matter. Do what you want. I don't care. I should have done I should have done Nadaraya Watson as well. See if it worked. It'd probably be perfectly good. Okay, so they all have different capabilities. Remember, lock-fit allows censoring, heteroscedastic weighting, and outlier rejection, and lock-fit's more powerful, I think, than most of them. So I think if there was one of them I'd recommend lock-fit with local bootstrap resampling for the confidence bands. So, ladies and gentlemen, I've done it in 50 minutes. I usually do a little slower because I'm usually speaking to astronomers who don't know anything. So in 50 minutes, I gave you a lecture on smoothing, on kernel density, histograms, kernel density estimation, and adaptive. You may notice, you might say, where's the one that's adaptive? It's not there. And I just found Abramson's adaptive. I'm going to have to put it in the book. I put it in the exercise. Okay. But for some reason, statisticians don't actually do adaptive smoothing, but astronomers really need it. We really do. We really do. We often have heterogeneous time series or heterogeneous images or heterogeneous random variables where things are smooth in some places and really, really complicated and collected somewhere else. And we really need adaptive smoothing. So I would personally say the statisticians do not have their act together on adaptive smoothing. Okay? Whereas you have too many methods for regular smoothing. There's so many options, it's ridiculous. Now I have no idea why in the last 5 years young astronomers all use something called Gaussian processes of regression, and not the others. Okay, I just don't know. But the good news is that there's quite a lot to it, and the applications are sophisticated in astronomy. So at the moment, I'm giving, this is session 4 of a 15-week semester. So I'm giving an introduction. I'm giving overview, and I'm not doing anything research level. It's just like little exercises. But later on, you're going to have 2 classes where 2 of our scholars, one of whom's in the room, David. Oh no, 2. Both of you and all 3 of you are here. The 3 of you, David, Tuck, and David, are going to stand up here and give a much more sophisticated and advanced treatment of Gaussian processes regression for specific real research problems in astronomy, and they're going to teach us more. And I'm going to take notes because I don't know enough about it, and I need to know more about it. Okay. But now that you've heard my general lecture, maybe you can hark back to it a couple of times and say, hey, this is sort of like a cross-validation estimator or something. I don't really know what you're going to say. So it'd be interesting to see how you link what you're doing with, Bernard Silverman's introductory textbook that's been around 30 years. I don't know the answer to that. But often in statistics, the methods are connected to each other one way or another. And I just don't know enough to know how the work you're going to present is going to be connected to these more elementary things that I'm showing here. But I look forward to it, gentlemen. Unfortunately, this might be one of the days that I'm not here because I have to go back to Penn State for a month. But I assure you, I'm going to watch the video. So the video will appear, and maybe that same evening, or very shortly the next day, I'm going to look at the video. So even though I'm not physically here, pretend I'm here. Okay, I really want to learn. I really do. Okay, are there comments then, ladies and gentlemen, on this? On 1,000 ways of smoothing your time series or other low-dimensional data set using random or fixed variables. Did you learn something? I was surprised how much I learned. I was surprised how many similar ways there were to do this. I thought, oh, there'll be a smoothing procedure. And it's not true. There's dozens of smoothing procedures. Splines alone has a stack of books up to the ceiling, and that no one reads anymore, I don't think.
Is there any measure to see which one is the best?
I have no idea. I don't think the word best has a definition. I think in some cases, when they say minimize the me's, that gives you a best bandwidth. In some cases, say we're going to use the AIC to help prune the knots, some sort of likelihood-based pruning, and Bayesian adaptive regression splines. Again, some sort of likelihood-based concepts, procedures. So I think the answer is, I'm glad. I'm glad that people have me's that they're minimizing and likelihoods that they're maximizing. But there doesn't seem to be a consensus where everyone's converging and saying, this is the one way everyone should do it. And then there's Lois, who gets more hits than anybody else on Google. And I don't know what he does mathematically. I don't know if he's maximizing a likelihood or just sort of glomming on different procedures till it works very well. I don't know. So if when you guys present Gaussian processes regression, I hope you'll remember this class and, to start somewhere where we are and teach us what that method is and why it's a good method. My personal guess is it's a perfectly good method, except for the Gaussian hypothesis, and which can be tested after you do it. You just take a look at your residuals and see if they're Gaussian distributed. So you'll know whether or not it was an appropriate decision. So I'm a little confused myself. I don't know what to do with so many different essentially redundant methods. And if you ask me to recommend something, I basically can't. I basically can't say, oh, I confidently recommend something. The person I would probably ask is David Rupert, because he's now spent a couple years speaking to astronomers, and he wrote one of the books. And so I'm really waiting for David Rupert's book to come out and see which R codes he recommends. And he has his own. I'm sure he'll have his own package. But which methods he's going to recommend? Because he's a brilliant guy and experienced. He's more my age than your age. Rupert's been around a lot. So I'm very interested to know how he threads the needle here. This is one of the problems where it's not as though it's really hard to find a method. It's one of those where it's really hard to choose among too many methods. And I think they all have subtly different capabilities, but I don't know that much. Okay, it's 5 minutes. Any comments, further comments? Okay, so this first hour was called smoothing or density estimation. And we did both a little lecture and art. And now we're going to break for a few minutes. And we'll go have coffee. And the good news is that I brought cookies. Yay. And then let's say a few minutes after 6, 10 minutes from now, we'll come back here. And we'll do time series, only R, no lecture. And sort of advanced stuff. It's more like, I'm going to wow you with, whoa, what's that? And oh, what's that? And I'm not going to be able to explain it for two reasons. A, I don't have time. And B, I'm sort of stupid. I don't know enough to explain them all. Okay, so that's sort of not the right way of teaching. I should teach slowly and carefully and thoroughly and explain everything. But in this particular example, between 6 and 7, we're just going to analyze a few astronomical time series in like a dozen ways and sort of say, oh, wow, okay. So maybe when you do your project, you might say, ooh, that's cool. I'm going to spend my project doing imputation because that was cool. Okay, so maybe this will guide you or interest you, tempt you. Okay, let's have coffee. I'm going for coffee and cookies. Okay, ladies and gentlemen, please open up 4timeseries.r. And there is chapter 11 of our book, but our book is now several years old, and most of this is not in the book. So most of this is for you. In fact, some of it, you're the first people ever to see this in terms of students, which is another way of saying it may crash. Okay. So let's start with an irregularly sampled time series, which those of you who are at SAMC this year know this is a major, major research challenge. Okay? So in this case, I have a star with radial velocity data. I wonder how many data points I have. Length, RV, column 1. 138 data points. It's not a very big data set. Okay. So I found one of the problems that I have time. I have a measurement called velocity. But I also have the error bar on the velocity, heteroscedastic measurement errors. And R does not deal with it in terms of plotting, so I found a package in H miscellaneous that does error bars. So this is just to plot the data with the error bars. And there it is. Astronomers are used to these kinds of plots with heteroscedastic measurement errors. Statisticians are not used to these kind of plots. For the statistician, we actually measure the measurement error. That's not the error of the star, that's the error of the accuracy of our measurement. And we measure it carefully. You might say, how do we do it? And the answer is we built the damn instruments. We're very, very careful. We actually spend a lot of time studying the process of our measurements so that we know the accuracy of every single measurement. And it can change by a factor of 10 between measurements. Okay, the first thing I'm going to do, I forgot to say, as you will see in just a few minutes, this has a periodicity to it. Now if you look at it, I don't see a sine wave in there. It looks like, I don't know, just scatter. Some of the scatter's measurement error, but most of it's not. And the answer is that the periodicity is hard to find. And we're going to run periodograms and try to find it in just a minute. But also, what's periodic is not a sine shape. It's not a sine or a cosine. Instead of not a lumpy, it's asymmetrical. And we astronomers are also astrophysicists, and we understand that because this is a planet with an elliptical orbit. We actually understand what we're doing. But if you happen to know some of the visitors like Rebecca Dawson, Eric Ford, Jesse Sajewski, they're the ones who are fitting these elliptical models to the radial velocities, and others here probably are doing it. But I'm not going to do that here. I'm going to run R sort of non-parametrically. And there is a non-parametric density estimator of the data that has been folded. We call it folded. You would call it, the times are modulo 62.257 days. And how do I know that? Well, I read it in an article. The article said the period of this planet is 62 days. So that's how I didn't derive that. I just read it. This is the modulo symbol. 2 percentiles symbols is modulo. How do you know that? How do you know what modulo is? You say help. I think you need quotes. Percentiles. It ends up it's 1 out of about 8 binary operators. There's plus and minus, times and divide. That's the easy ones. There's exponent. Then there's modulo, and I don't know what that one is. You know what that one is? I don't know. Something related to modulo. So now this is real astronomical data. So as you can see, the local regression, and if I ran any of those splines and any of those others, they would all do more or less the same thing. It actually goes up and down fairly nicely, and it has. This is actually a locally estimated confidence intervals, so the band is not a constant width, it's actually going up and down. But in this particular case, it's not doing much. And the only question is, did I do something with the outliers? I'd have to look at my code here. I chose 0.5 nearest neighbors, and I chose to do the heteroscedastic weighting by the variance, the heteroscedastic variances, but I didn't choose to do outlier rejection, something called M estimation. So again, there's many bells and whistles in LockFit that I could use. In this case, I used the weighting option of LockFit. So LockFit is very, very useful for astronomers. Astronomers, in my opinion, should be running LockFit with this weighting all the time. It's really cool. Very useful for astronomers who know their error bars. Okay, now how do I find the period? Well, if it was evenly spaced data, I'd run a Fourier transform, a FFT, a fast Fourier transform. But it's unevenly spaced, so I'm going to run a generalization of the Fourier transform. It's actually mathematically derived as a least squares to sines and cosines, as a least squares regression approach. Although the actual calculation, I believe, uses FFTs in a clever way. It's known as the Lohm-Scargill periodogram. It's extremely famous. A couple thousand citations in astronomy. And Jeff Scargill is one of the most famous astrostatisticians in the world. And has Jeff been here? I don't think he... Is Jeff here?
The opening workshop?
At the opening workshop. Good, good. So Jeff is the most knowledgeable time series analyst among astronomers for 40 years. Jeff is a really good guy. He's a friend of ours, and he's has many accomplishments and talents. So LSP, Lohm-Scargill periodogram, sitting in this package called Lohm. And what did I do? I said, well, give me a range, so I can't do an infinite number of frequencies. Give me the two columns of, in this case, it's not weighted. And alpha equals null. I don't know what that does. Let's try to find that out. LSP. What's alpha? The significance level. The periodogram shows. Oh, I don't believe the significant level, so I didn't put it in. They're not believable in most cases. So I said, don't give me a and then that's the correct period, apparently. Or correct, that's the period that's published. You can see the Lohm-Scargill is slightly off. I don't know why it's slightly off. Anyways. So as you can see, when you have only 123 points and they're irregularly spaced and they're noisy, that you don't get the world's cleanest power spectrum. A clean one would be just a little bit of noise and a single sharp peak, and the rest of it is noise. Instead, what we're doing is we get noise, but we also get aliases, probably beating with probably a 24-hour beat, but I don't know. I'd have to check. And these other structures is very, very, very non-Gaussian. All power spectra do not have noise structures that are calculable in practice, only ideally, and it's never realistic. Okay, so thank you very much for Lohm, but it ends up that a German master's thesis in applied math was written a few years ago, fairly recently, that actually somehow they heard about astronomy in this university in Germany, and they wrote a package called RobPer, robust period. It's not necessarily robust, but it's really cool package. And they actually did a lot. So let's see how I set it up. I said, okay, give me a sequence from 1 to 1,000 in 10,000 sort of very accurate periods, and then give me the frequencies for them 1 over the period. I could use 2 pi if I wanted to, and then make me a 4-paneled figure. MF row 2 is the way of getting 4 panels. And for those of you who actually want to publish things, often the default of the multi-panel system in R has a lot of white space in them. So you got to fill with these other margins to make the white space look good on your screen and in your figure, so you can publish it and it doesn't have too much white in it. Okay, the first one is by Schwarzenberg-Czerny, who's an astrostatistician for many years from Poland. And he has a periodicity method that's related to analysis of variance. And I'm now going to run it. In this case, I'm doing heteroscedastic weighting. Weighting is true. I'm doing an L2 regression. That means it's a least squares. I'm taking 10 steps of his algorithm. I don't remember the algorithm. And it's finished. Okay, good. It took a few CPU seconds, that particular one. And now I'm going to plot for those 10,000 frequencies, I'm going to plot the power, and there it is. And there's that arrow in the same spot as before. And you can see that this particular one, when you went to lower frequencies, longer wavelengths, it started showing a forest of spurious peaks. And this is because it's a short data set. It is not infinite. It's irregularly spaced. It's not evenly spaced. And it has non-Gaussian scatter, heteroscedastic measurement errors, has all these problems. And the different methods, we're going to put 4 panels up, you're going to see, are going to treat them differently. And they all have arguments for them, but they're different. I would say if anybody is interested, a statistician that is in the room, for their project, to look into the math behind these different methods and sort of discuss and evaluate them. This one's the one with the most citations in the astronomy literature. It's called a phase dispersion minimization. It's a variance-based periodogram that is sort of non-parametric. It doesn't assume Gaussianity. Well, maybe it does. It assumes Gaussianity, but it doesn't assume a sinusoidal shape. It's calculating 10,000 of them. And there we go. There's the PDM. Came up over here. And it actually is quite similar to the AOV. It's not identical, but it's pretty similar. And that one has a couple thousand citations in the astronomy literature. Since 1977, it was written down by an astronomer named Stellingworth, who's never not been known for anything else that I know of, except this one methodology paper of great utility. The next one is an L1 solution using a sine wave. We know it's not, the sine is not the best option. And here it is. This one you can see had much less signal at the low frequencies, but had worse aliases and nearby. And maybe not even worse. Maybe this is a better one. This is L1 in the sense that it is least absolute value rather than least squares as the underlying statistic. This one is not famous. And here's one that is a generalized cross-validation method. I don't know the math behind this one. Oh, model equals splines. It's an L2 spline with heteroscedastic weighting and with cross-validation. I don't quite know what it's doing in cross-validation. In my opinion, it didn't do a very good job. It has all sorts of hash in it. And if you compare these with the Lomskargel actually did a nicer job in some ways. We're going to see this program again in a few minutes, so I'm not going to talk more about it. But I want you to know that RobPer was not around 10 years ago. It's a relatively new package. It is made for astronomers, but oddly enough, it's not by astronomers. It's by a young mathematician in Germany. So I called her up. I wrote to her email. And I said, oh, I really, really, really like it. It's really important. And she wrote back and said, I'm sorry, that was a master's thesis. I'm working in industry. I'm not working on it. Goodbye. So it's version 0.1, and it will always be version 0.1. It's one of those unmaintained grand packages. It's pretty funny, isn't it? I don't think she has any idea how useful this is to astronomers. Okay. I don't know. Anyways. Okay, so that was a irregularly spaced, periodic, non-sinusoidal, heteroscedastically weighted period search. And if you happen to know something about astronomy all of those words, all of those problems are common in astronomical data sets. And there are people in this building this year at SAMSI, some of them are in the room, who are working on the statistical methodology for these kinds of data sets. So that's why I wanted to show you one. Okay, now I'm going to do something else. Ready? I'm going to read in this Kepler-1 DAT and this Kepler-2 DAT. This is from a satellite which did much nicer data, okay? It has evenly spaced data with 77,000 points per object. And very, very precise and not heteroscedastically weighted. Just, every point is equally weighted approximately with almost no outliers. Oh, there's one outlier, I take it back. There's one outlier. That point there is a bad point, it looks like. And it's evenly spaced. Every 29 minutes for 4 years, there's a data point. So that's 70,000 evenly spaced. So this is the kind of time series that a statistician wants to see. Evenly spaced, homoscedastic, and a lot of data. Not just 123 points, but a lot of them, tens of thousands of them. The only problem is there are some gaps. The gaps are not bad. It's about 15% of the timestamps have not available in this data set. So it's not that bad. Here it is. I did that. What's the length? Here's a little bit of R. Okay, I got to read this backwards. This actually has 3 functions embedded together. First, I said take the first data set and give me a vector from the values that is just a vector of true false of whether it's an NA or not. Is it a real number or is it NA? And then tell me which ones those are and tell me the length of that. And that tells me, and then divide by the total length. That's the fraction of the length which are not available, and it's 16% for the first one. It's worse for the second one. 29% of the data of the second one are missing. And you can see it. Something happened with the satellite, and it didn't measure or make all the measurements on the second one. Satellite only cost $700 million. That was a joke. Okay. You'd think for $700 million we can get the data. Okay. But I do want to tell you that we have 200,000 of these light curves from this one satellite, and that these are the finest, most accurate, most precise data ever obtained by humankind, by astronomers in the history of astronomy, in terms of what's called photometry. The time series of the brightness of stars is this data set. It's a beautiful data set. So you may complain about it, but more typical is the first data set, 123 points. It's all full of problems. This is much nicer. Okay, so now we're going to go through a series of our commands and actions that are just Kepler-1, and then I'm going to do a series on Kepler-2, just exercising. Okay. Okay, the first thing I'm going to do is I'm going to say, hey, what's the median value and what's the interquartile range? These are non-parametric measures of location and spread. If I knew everything was Gaussian, I'd say mean and standard deviation. In fact, I wonder if I could test the Gaussianity of it. I could test it. I'm not going to do it right now. The important thing is the recognition that the stars, it's not the data, not the instrument, it's the stars that are being measured, are autocorrelated in their variations. They go either or something like that. Sometimes they're quasi-periodic, particularly the second one we're going to see is quasi-periodic. And some of this is understood. So here what I've shown is the autocorrelation function. Now I gave a lecture last time with all sorts of basic concepts and some basic math, and the autocorrelation function was there. There it is. The autocorrelation function in this case is incredibly flat. It's very significant, those little dashed lines. Everything is above the dashed lines. All of it's significant, and it doesn't decay. It means it has long memory processes, which is nasty for time series analysis. And this is the distribution of the values, and it looks pretty Gaussian. So that's nice. So I thought I would fit it with a Gaussian. So it ends up the function to fit there's 20 or 30 or 50 or something statistical distributions built into R, that are easily found, and this program called fit distribution. That function is in a library called mass, which is built into R delivery, and so we can fit it with a Gaussian, and then we can use the curve function to plot the Gaussian that comes out of the function, and look at there's the plot. There's 77,000 points. Oops, it's slightly asymmetrical. See that? It's a little off over there, not by much. I think it's pretty good. It got the tails very nicely. It has beautiful Gaussian tails. It's just sort of in the middle. It's not a little lumpy, not quite Gaussian. And because it's 70,000 points, when I run a non-parametric test, what's called a goodness of fit test, in this case I run the Anderson-Darling goodness of fit test in a package called normal testing. There's like 10 different tests for normality in this one. This one's one of the most famous ones. It ends up it's extremely significantly not normal. Less than 10 to the minus 16 p-value. So that tiny little deviation is statistically significant, but scientifically, it's not a very big deviation. And really, it's really pretty amazing that you can have a data set that has enormous amount of correlated structure, but yet has Gaussian scatter. And it's sort of a weird combination of niceness and unniceness. I have no idea. I didn't design this data set. This is the star, okay? The instrument didn't do this. This is the star. The star just has this star has those characteristics. The next star will have different characteristics. Yeah.
About the fit distribution.
Yeah.
Why not just, what's wrong with just taking like the empirical mean and standard deviation?
I did the median and the IQR. I could do the mean and standard deviation.
No, for putting in, for plotting.
Oh.
Like, is it doing something more sophisticated?
Yes, it is doing something more sophisticated. It's doing an MLE. It's doing every single one of the 77,000 points is contributing equally. It's not using what's called method of moments, which is what you suggested. It's being much more sophisticated than that. This is the MLE. So if there's one tail on the left side, we'll pull it all over. Whereas if you use just the method of moments, it will ignore the tails. It will ignore almost everything. So it went so fast you didn't realize, but it did a maximum likelihood estimator of a nonlinear function of 77,000 points. And it did it so fast you didn't notice, but it did it. Fit distribution is a nice program. I'd like fit distribution to allow arbitrary functions, but I don't know if it does. You have to write your own maximizer called optim for your own personal functions. So another one is I'm going to go through the data and I'm going to run a correlation test to see whether or not there's any trend. And you would think there would be. Where's the data? Oh, I lost the data. I overwrote it. But when I looked at the data, it sort of looked like it was pretty flat. It didn't have to be flat. That wasn't built into the data set. It was the star. So it's now running. And for some reason, a bivariate correlation test is taking CPU time. I don't understand why this is so slow. It's a trivial calculation. I don't understand why this is slow. Oh, finished. So it ends up, there's a p-value for this. It is it is completely insignificant. There is no correlation at all. There's no trend whatsoever in this data set. In other words, the mean it's not exactly 0, but it's very close to 0. Every part of the time series has the same mean. There's no slope or trend to it over the whole data set. So this star was incredibly constant in mean Gaussian in scatter, but highly autocorrelated. It's a very, I don't think any time series analyst would ever dream up this combination of properties. But these stars are interesting. I mean, they literally have different characteristics, and this one has those characteristics. I'm not intelligent. I just chose this one randomly. Okay, now I'm going to run an autoregressive model called ARIMA. And this is the one you're going to hear a lecture on later on, just like you'll hear a Gaussian processes lecture. You're going to hear an ARIMA lecture. And the person who's going to give that lecture is me, because that's my research area. So I'm teaching at the moment, but I'm going to pretend to be a researcher later on the semester. And that's going to be towards the end of the semester. I think it's April. I'm scheduled. So I just ran an ARIMA model. It's actually a global parametric model, but it's sort of weird. It's not like a polynomial. It's not a function of time. It's a function of the differences, x sub I minus x sub I minus 1, the differences between adjacent or lagged values. And it's a linear model of dependency on those. And that's a sort of an odd concept. So let's look at the structure of what comes out of an ARIMA fit. It's a mess. It's a lot. It's a list of 14 things, and there's a hierarchy of model coefficients and all these different bells and whistles. And these things are not simple. I mean, it may have taken only a CPU, tenth of a second, but it's doing a lot of computations to do it. This one is an MLE, another MLE. It's another maximum likelihood estimator. So now I'm going to do the autocorrelation function, not of the data, but of the residuals after the ARIMA. And that's in my lower panel, the last panel of this. So you compare the top panel is the data. The bottom panel is the residuals after I ran an ARIMA model. It's almost perfect. It's almost all within those two dotted lines that are the 95% confidence. In other words, I have white Gaussian noise after I did an ARIMA model. So whatever's going on there in the star, the star knows about ARIMA mathematics. I have no idea why the star knows about ARIMA models. I mean, ARIMA's dreamed up by some mathematician, applied math person 50 years ago or something. The star seems to know all about it. It's perfect. It just blows my mind. I don't understand these stars. I mean, you understand, I've spent years studying these things. I don't understand them. But in terms of time series analysis, the Kepler data set is the richest high quality data set there exists. It costs $700 million to get it. And it's just a wonderful laboratory for time series analysis. And of course a laboratory for trying to understand things. The goal, by the way, is to try to find planets around the stars. And we're using the ARIMA models just to get rid of the stellar variation to look for the planets and the residuals. So let's do some diagnostics. Now most of you have it is doubtful you have seen much of the next material I'm going to show you. So the first diagnostic is to say, are the residuals normally distributed? And that one you've seen. That one's called the Anderson-Darling normality test. And the answer is it is not normally distributed. So they're consistent with Gaussian white noise, but they're not Gaussian white noise. Now, this one is going to, the next one's required an evenly spaced data set without any NAs. So I'm now using a code, which I'm not going to talk about right now because I'm going to talk about it in about 10 minutes or 5 minutes when I do the second star. I'm going to impute the missing data, called imputation. I'll describe this later. It's really cool, by the way. Now I have a complete set of residuals without any missing values. So what am I doing here? What am I doing here? Oh, I wanted to do a Durbin-Watson test. So Durbin-Watson, Durbin's a Nobel Prize winner in economics like 50 years ago. obviously was a brilliant mathematician. There's many, many things that are in statistics and time series that are named for Durbin. And so I wanted to test for correlation. That's a significance test, a hypothesis test. But it ended up that this particular code was very annoying. It wouldn't accept this vector of residuals. I had a perfectly good vector, and it wouldn't accept it. It only would accept something that was in something called class LM from linear modeling. So I had to fake the system. I put in garbage, created an LM object with garbage, just completely arbitrary, and I put in the vector I wanted in the right spot, just so I could get this thing to work. This is an example of when you're trying to patch together different things in R and CRAN, sometimes you got to be a little sloppy, and this is definitely sloppy. I didn't code it very elegantly. My coding was like, let's just throw it together and stir the pot and see if we can get a number out of it. So now we're running the Durbin-Watson test, which is a test for serial correlation, and for some of the residuals, the ARIMA residuals, and that took several CPU seconds. And the answer is there is no serial correlation. It's uncorrelated. Now, I'm a little confused. Why did the Anderson-Darling test fail and the Durbin-Watson succeed? I don't know the answer to that. But there's 3 zeros of autocorrelation. There's no autocorrelation. Oh, serial. Oh, serial autocorrelation means lag of 1. It's good. It's the AR1 model or the MA1 model. Maybe it's possible to have no serial autocorrelation and still be non-Gaussian. It must be possible. This is the kind of thing with time series, like, whoa, it's like really weird. Okay, so now there's a test for independence called the Box-Pierce test or the Lejeune-Box test. This is the same Box who was R.A. Fisher's son-in-law. In this case, it survived the test for independence. Now I'm going to do a test for stationarity. This is in another econometrics package called TT series for time series. And I just ran the augmented Dickey-Fuller test, which is completely unknown to astronomers, but is very well known to econometricians. This is a test for stationarity. And the answer is 1%. It's just slightly non-stationary, the residuals, but it's pretty close to being stationary. And then I'm going to run another test that seems a little rarer, called the BDS test, for 3 people whose initials are BDS, which is a test for independence and identical distributions, which is not quite the same as independence alone and not quite the same as Gaussian distribution. It's a separate test. All of these are different hypothesis tests developed by econometricians to characterize time series, to see how far they deviate from sort of a nice, basically Gaussian white noise. And this particular one, wow. Yeah, I don't know what's going on. Oh, I was wrong. The ADF was not CPU intensive. This one is. I never found anyone who uses the BDS, but the ADF is widely discussed. If you type in augmented Dickey-Fuller, you'll find Wikipedia pages, you'll find graduate courses, and every business school talks about it, has lectures on it. It's a big thing. I'm not quite sure why it is. You remember the word stationarity? I gave a lecture with some concepts. And stationarity means whatever the weird behavior is, it's the same in the beginning, in the middle, and the end, but I'm not going to characterize the behavior. And so basically this particular ARIMA residuals is very well behaved. I mean, it survived the Durbin-Watson test and the Box-Pierce test and the ADF test, and it's basically very, very close to being white noise. And a lot of what time series analysts do is they take some weird time series and they model it until the residuals are white noise, and then they stop. And that's sort of a style, a very common style of time series analysis. by engineers and by econometricians. I'm not sure about statisticians. Oh my, this was a bad idea. I should have stopped this. I did this in my office, so it will, in fact, end on my computer sooner or later. So one of the things I'm trying to do is I'm trying to bring to the attention of astronomers these established methods from econometrics, from time series analysis. They're taught in business schools and in engineering schools. Maybe they're occasionally taught in math schools. They're graduate level, methods. They're not simple. And in this case, the p-values are all 0. I don't know what this means. I don't know what this means. Help BDS test. I really should take this out. If I don't understand it, I can't put it into the tutorial. Examines the spatial dependence of the observed series. To do this, the series is embedded in a higher dimensional space, and the dependence of the values is examined by counting the near points, some meaning of the word near, with an arbitrary epsilon. And this test statistic is asymptotically standard normal. Missing values are not allowed. That's why I had to run an imputation on it. Okay, there's a print method. Print. Okay, I can't do it. Okay. I don't know what to say. I'll say I should take this out. Okay, let's go to another one. This is the one that had a lot of gaps. I don't know if you remember it. I'll show you that in a minute. But now I'm going to run this imputation, and we're going to really look at it. So I'm installing the package again. Okay. Oh, that was fast. It gave me a warning message. Now, errors appear in red. If it says error, it means it crashed. It didn't run. If it says warning, it means it ran, but you should be aware that there's a problem. And you can actually type in warnings, parentheses, and it will tell you the recent warnings that you got. Sometimes you get 100 of them. And you can look at them all. So Optim is a numerical optimizer. The default is a simplex for nonlinear functions. It finds the maximum of nonlinear functions. And so it didn't converge well. So abnormal termination in some subroutine because of it's a convergence problem. Okay. So I ran this. Let's now look at this. Help na.common. What did I actually run? Oops, I ran some sort of a model. It's in a package called impute.timeseries. Impute time series. The title is Missing Value Imputation by Kalman Smoothing and State Space Models. Okay. And the model it chose, unless you tell it otherwise, is ARIMA, the same model I happened to use before. Auto-ARIMA is a clever version of ARIMA where you don't have to tell it. I tell it, please give me 2, 1, 2 before I told you the order. How many terms in the polynomial, essentially. Now it says it will determine by itself how many terms to use using
the maximum number, I think, right? Something like that.
the AIC. I'm sure there's a lot of parameters to this calculation, like the maximum order and this and that. But this is a well-known approach to modeling stochastic time series is ARMA modeling with AIC model selection. And in this case, it worked great, as you're just going to see in a minute. Okay. And so if I really want to read this, I should read a SIGGRAPH course from '95 and a book on forecasting from 1990 and a book from 2011 on Kalman filtering. So if I want to And those books are just a good starting point. You understand? The guy just gave me 3 graduate textbooks to start learning this, what this code is doing. So it's like a complicated business. It's really fairly complicated, okay? And here's the reference I'd put in my textbook. Hindman and Kondak are automated time series forecasting, the forecast package for R. That's the journal with R codes, essentially. And this person is well known. Hindman has written several books. He's one of the world's most prominent. He's a professor of statistics in Melbourne, Australia or something. He's written many books, several books, and the forecast package is AutoRima. That's him. And so I think even though it's used for econometrics, he's a professor of statistics, not of economics. His book, oh, you want to know? His book on forecasting is an e-book, which means you don't have to buy the book. You can read the chapters online. That's really cool. Called Forecasting. It's not this book. He has another book called Forecasting. Oh, that's a different author. It's a huge field. Okay, so what did I do? I ran this NA common, and now I'm going to make some plots. Okay, until I do the plots, you're not going to see what it does. It really does like the world's most amazing job. There it is. So now I'm looking at a part of the original time series. It actually is sort of periodic, but it's actually not strictly periodic. The shape of the periodicity is not a Gaussian, it's not a sine wave. It sort of looks like 2 or 3 sine waves, but it's not constant with time. The amplitude is not constant with time. So it's a quasi-periodic behavior in the star. Now I understand that. I know about this star, I think. It's a rotating star, has a spot on it. The spot comes and goes, but it has 2 or 3 spots, so the spots come and go and you get 2 or 3 lumps. And then the spots don't last very long, they die away in a few months, so that the shapes change. And sometimes the star is really quiet and sometimes it goes really crazy. And not only that, but the star can be rotating differentially, so if the spot's on the equator, it may have a slightly different period than if it's near the pole. And how do I know all that? I don't even know the name of the star. Because everything I described is in our sun. The sun has sunspots that look just like this behavior, but very weak. So this is really, really weird. And why the satellite happened not to get good data in here, I have no idea. So what this is a smooth curve of the imputed values superposed on the same data as there. And look how nicely look how it's smooth. You see it's sort of spotty data. And then look at this one right here. There's no data at all. And it went down and up nicely. Look, no data down here. Down and up nicely. Look at that. Down and up, down and up. Imputation. The ARIMA imputation is like really nice in this case. It's very smart. If you wanted what I would do, I'd just do a linear interpolation. I'd go from here to here, go zig like that. It would look terrible. So, maybe I'd be clever. I'd do a cubic polynomial. It wouldn't look very good. Wouldn't look very good. Cubic polynomial is terrible to fit any of this. The ARIMA is just amazingly good. And then I'm using it to fill in the gaps, to impute the missing values. I'm actually curious for 1 second. Structure, Kepler 2 _ impute. That's what I called it myself. Oh no, that's just the values itself. I want all the details. I want to know what order it was, what order ARIMA it chose. I'd have to dig it out somehow. I don't know how to do it. Okay.
Like summary or something?
Each author writes their own summary the way they want to, and sometimes they're really informative, and sometimes they're sort of stupid. It's just a vector. 71,000 data points. Didn't do anything. Okay. So now I'm going to go and do something we did with Kepler 1 star, but this is Kepler 2 star. Where I'm going to run a Fourier periodogram on the complete data set where there's no missing data, so I can run an FFT. So this is a very basic program in time series analysis in R. It's actually in R itself. You didn't have to do any packages. It's called spec.pgram. Pgram is periodogram, spectral periodogram. And I had to say, give me a range of frequencies, and then I smoothed it and I tapered it. In this case, I didn't taper it, I taper 0, and I labeled it Fourier. So this is my Fourier spectrum. It seems to have 2 broad peaks in it, and then the next one is going to be a Lohm-Scargill periodogram, LSP, from one of the other packages that we used just a few minutes ago. And it shows the same 2 peaks, but much cleaner. Look how nicely the Lohm-Scargill did. I don't quite know why this one looks so much worse than that one, but the signal to noise of the peaks is just enormously better. And then I'm going to go and do one of the 4 that I showed before from Robper. The German package. I'm going to do the one called phase dispersion minimization, PDM. And this is CPU intensive. Okay, well, just wait a minute. So it's doing an L2. It's not weighting the data. It's taking 10 steps. I don't quite know what the 10 steps are. I think that might be 10 bins in the folded periodogram. I'm not sure. And it's actually computing here. It's at least a double loop. It might even be a triple loop over 70,000 data points. So it's computing. It's thinking. It should finish sooner or later. I did it in my office earlier today. It seemed to work. So one of the things that astronomers are having, let's not use the word trouble. Why don't we just say they can't quite decide which periodogram to use in what situation? So some may use Fourier, and some may use the Lohm-Scargill periodogram as the most commonly used. But it doesn't have, I don't know. I discussed it a little bit last week. It has some theorems behind it. But Jogish doesn't think it's that great all the time, and he's a mathematical statistician. It's not obvious. It's not obvious what you want to do. And no statistician has looked at the PDM and evaluated its bias or variance or characteristics. And so you get these different periodograms for different stars in different data sets, in different methods, and basically the community doesn't know what to do with them. We're confused. We need help. My poor community is floundering in methodology world when it comes to, particularly for irregularly spaced data sets. It finished. Okay, so this is the PDM. It got the peak, it got the secondary peak, but it got this terrible forest of low frequency harmonics or aliases, I guess they're called. And I don't know why the PDM shows those and this doesn't. If somebody here wants to do a project starting with this data set and trying to understand these methods, and there's 2 or 3 others that are sitting in Robper, it'd be really cool to try to figure out mathematically why these look different. I just don't know. I know that astronomers fiddle around. They say, hey, the Lohm-Scargill looks the best, and they publish the Lohm-Scargill. But that's not based on any, it's not based on any mathematical reasoning. It's just, hey, let's publish. Okay, so in this case, sometimes I don't like what the astronomers do, and I think I know what the statistician would recommend. In this case, I do not know what the recommendation would be.
So how do you decide the upper limit is 0.005? If I use a larger number?
Oh, I think this is just the range of frequencies I just happened to plot. Okay. This is not a significance level. It's almost impossible to establish significance levels on any of these periodograms. Astronomers try, and it's almost always wrong. And if someone wants to come and visit me, I can try to describe some of those problems. But it's very difficult to evaluate, let's say, the significance of the secondary peak. Is it really there or not? It's very hard to know. Okay, let's now move. Whoops, I should say Kepler 2. Sorry. Well, we're almost ready. We're almost finished. It's also 2 minutes to go at the end of the day, so I'm going to go fast. I'm going to take the imputed values, and I'm going to run a discrete wavelet transform. And I'm going to show 3 plots. Forgot what the 3 plots are. Let's take a look. Wavelets are really efficient, so that, oh, wow, it's done. It's all done. So these are plots as a function of time along the data set. Let's look at this longer one. You can see that as the spots come and go and the amplitude shrinks and stuff, we're seeing that for this longer time scale wavelet, sort of fatter wavelet, we can see a lot of structure, autocorrelated structure, in fact. And here's a intermediate sized wavelet, and here's a teeny weeny wavelet. So that means right in there it's sort of noisier on very small scales, while it happens to be quieter on long scales, whereas here at the end it's very, very noisy on large scales and surprisingly quiet on short scales. And so wavelets are really powerful. I mean, you really learn a lot from a wavelet analysis. I mean, it depends on the data set and what the problem is, but it's really highly informative. But I don't know of hardly any sort of established ways of interpreting these graphs. You know, it's like, oh, I just told a story. Oh, the variance is high there and low there, and that's sort of interesting. But to actually sort of quantitatively understand it, I don't really quite know how to do it. But I'm going to show you something absolutely wonderful about wavelets. Okay, it's called wavelet denoising. So what you do is that you see the really small values, set them to 0. Below a threshold, you set the wavelet values to 0, and then you go back and you do an inverse wavelet transform. So the top is, I just blew up a portion of the data set. That's the portion, same data set. It's the Kepler 2 data set. That's the original data. And you can see by the sort of grayness there, there's sort of noise in there. I don't think it's in the instrument. It could be the instrument or it could be the star. I don't really know, I guess. But I suspect it's the star, but I don't really know. It's not my business to know that. Okay. And then I set some wavelet coefficients below some threshold to 0. I just had to guess the threshold. I probably did it so it looked nice. And look how nice it is. Look how I denoised it. It's like gorgeously smoother. So first I imputed the missing values that way, horizontally, and then I denoised it vertically. And oh, that is just a gorgeous time series of my star. Wavelets are really powerful. ARIMA is really powerful. Time series analysis is books and books and books about ARMA modeling, ARIMA type modeling, and books on wavelet things. These are very powerful, flexible methods, widely used in engineering and econometrics. And I won't say never used by astronomers, but they're not in our familiar toolbox. The only thing we're familiar with as astronomers is Fourier analysis. And that's why we like Lomb-Scargill. I'm not saying Lomb-Scargill isn't good, especially when we have periodic phenomena. All I want to say is the repertoire is vast in time series analysis. And the repertoire in R and CRAN packages is huge. And if you're skilled, you can just do marvelous things. So notice how skilled I am here. I've iterated these tutorials. I mean, I can't do this again on something else. Okay, so I seem, oh, look how professional I am. I'm not really very professional. Okay, I'm sort of, I know some of the stuff, and I made the tutorial look good, right? So I went from here to here because I tuned it to make it look good. But do I really know how to do an exploratory wavelet analysis so that you learn everything there is to learn about that unusual time series? I'm not the right person. Jeff Scargill it would be the right person. And there must be a few others around as well. So it is now 7:02, so I'm going to stop. Thank you very much for being so attentive for 2.5 hours. We're all hungry, although we did have cookies. I think obviously I need a box of cookies every Wednesday. I will do that. Are Oreos okay? Okay, you don't mind if we just stick with Oreos? That's what I had as a child in New Jersey. Okay, so I guess I could be brave and maybe do rainbow or, what was it, mint? You said mint?
Green tea.
Green tea? Oh no, really? Is that what you eat in China? Green tea Oreos?
Yeah.
I'll see. In the American store, there were different Oreos. I have no idea if they had green tea. I doubt it. Do the people in North Carolina eat green tea Oreos? I doubt it. So I think they probably don't have it here. But I'll check.
It's also called mocha.
Mocha. Okay. I will look. Maybe I'll be adventuresome and we'll have some different Oreos next week. Okay. See you next week.